Welcome, everyone. My name is Greg Risteban from Olympus OSSA. I'd like to welcome everyone today to this webinar titled Advancements in Phased Array Scan Planning. This webinar will offer a chance for attendees to learn advanced scan planning concepts, the implementation of different phased array inspections, and the ability to achieve a better overall understanding of the benefits and limitations of phased array. Our presenter today is Curtis Dickinson. Curtis is a Level 3 senior instructor with the University of Ultrasonics. He has an immense amount of working and instructional knowledge of advanced UT systems and software, including automated and semi-automated systems. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. The chat panel will not be monitored for Q&A. If we are not able to get to your question during the live webinar, they will be addressed personally either by email or by phone after the event. Now, without further ado, I'd like to turn the presentation over to Curtis Dickinson. Curtis, take it away.
Well, hello, everyone. Again, this is Curtis Dickinson. I'd like to welcome everybody in and just give everybody my thanks for taking the time out of the day to sit in on the presentation and just kind of see what we have to discuss and present to you. Won't take up too much time with introduction just because I know that we're all busy and we only have an hour, so we'll go ahead and just jump right into it. The presentation that we put together for you came from a presentation that we did for last year's ASME annual conference. We did a short course over advanced scan planning methodologies. So we wanted to put this together as just a shortened version of that and cover some basic phased array scan planning methods specifically for weld inspections. So what we'll cover is just a little bit about what we consider a scan plan to be, talk a little bit about where scan plans come from, what information is involved, a little bit about perspective from our codes. What do our code books typically tell us about scan plans, what's required, essential variables, and obviously getting into how we actually implement that scan plan. In addition to that, at the end of the presentation, I'll take a little bit of time out of just the PowerPoints and the presentation that you're reviewing right now and actually show you how to implement some of that using two pieces of software, NDT Setup Builder, which is a scan planning tool developed by Olympus, and Beam Tool 6, which is a program developed by Eclipse Scientific. So we'll start this off with, again, just talking a little bit about where scan planning comes from and how we look at it and how we use it. Typically, when you talk about scan planning, it's always referred to or tied to specifically phased array. It's a big buzzword. You hear it all the time. You kind of have some idea of what it is and how you implement it, how you use it. But really, scan plan comes from what we do on a day-to-day basis in any ultrasonic examination. Anything that has to deal with how you implement a UT test, down to transducer selection, down to evaluating sensitivity or resolution characteristics. Or probably the best example I have and typically use is determining your skip distance for an angle beam examination. So when you approach the inspection of, say, a weld with angle beam shear wave, one of the first things that the operator or technician does is they take the angle of inspection that they're using and they measure back from the toe of the weld to ensure that they have proper coverage. So there's several different things that we perform, even with conventional UT, that we consider scan planning. It's just a little bit more involved when you try and take that idea and transfer that to a scan plan. So from the phased array perspective, what is a scan plan? What's the definition of a scan plan? The scan plan, as you see here, how we define it, is a documented inspection strategy to provide repeatability for inspections. From a technician's standpoint or perspective or point of view, the scan plan is just a series of instructions. What transducer do I use? What wedge do I use? What angles am I supposed to generate with the transducer? From their point of view, it's just a list of those parameters that they either enter into the instrument or they just reproduce. But the scan plan is much more than that. The scan plan is meant not just for that single inspector, but it's meant to be used for any number of inspectors or anybody else involved in the inspection process. It's meant to document how the test is being done and ensure that no matter who is carrying out that inspection, no matter who's looking at the data, reviewing it, or even analyzing or looking at the report, that everything's done in conjunction, everything's repeatable, everything is consistent. So while the technician looks at it more as an instruction sheet, we want to take a more broad view of the scan plan and look at it as a tool for making sure every stage of the inspection is consistent and repeatable. But there's a problem with that. And the problem with that is we have a lot of variability in how you set up your phased array inspection. So take what you're looking at on this slide for an example. You have, obviously, as you can see, a phased array transducer and a wedge sitting on a part. We can tell that we have two different beam sets here. In blue, we have what's commonly referred to as an E-scan or a linear scan. In red, we have what's commonly referred to as a sectorial scan. On the surface of that, you have the idea that, okay, we're inspecting this joint with two different types of beams. But if you take a more in-depth look here, there's much more variability to how this is being done other than just the fact that there's a linear scan, there's a sectorial scan. Why did the operator choose two different beam sets? Why the specific E-scan here with these particular beams? Why did he choose to send them this direction to the part? What angles did the operator choose for the sectorial scan? Is there any reason or any purpose for this range of angles and where they're going? You can also take that back to the transducer. Well, how did they configure and choose to use these elements and this specific transducer to do that? An operator will also look at this drawing and say, the scan plan is instructing me to place the transducer at about 0.8 inches away from the center line of the weld. How did they determine that? And then even more simply, you have the variability of the part in general. You have material thickness to consider, and you also have joint detail to consider. Hey, this looks like a format of some type of double V joint. Well, what if the joint geometry changes? What if it transitions from being a double V weld to a single V weld? We have quite a bit of information to keep track of, a lot of variables that we can change and still perform the inspection correctly. So what we need to discuss, what we need to talk about are what are some guidelines to building this scan plan and trying to help with the variability of that inspection. Okay, so we look at all of those items, we kind of put them into a list, and we go down that list one by one and look at each one and try to put more purpose to them. So instead of just blindly picking a sectorial or an E-scan, looking at those separately and asking what benefit are those going to serve to the inspection. So we have all these different variables to look at. Some end up being more important than others, but we just want to make sure that we don't overlook any one particular item, because there are certain things involved in the scan plan that do often get overlooked that still end up being important. So hopefully this process that we'll outline will give you a better idea on how to approach building the scan plan and actually using it. Because you'll notice that on this list, there are several things that you may not have considered when looking at a scan plan. In particular, the focusing effects and the transducer selection, which is, again, an item that often gets overlooked when you're building the scan plan. So we have all of this variability that goes into the scan plan, all of these different choices to make when it comes to putting it together and implementing it. And one of the places that we would want to go to hopefully get some perspective and get a little bit of guidance on putting that together is our codes. One thing that we should get from the codes is hopefully a list of some essential variables. So items that the code will list out that we have to pay particular attention to. So at a minimum in our scan plans, we should include that information that it outlines. So what is some of that information? We have some of the obvious ones: transducer selection, wedge selection, beams, number of elements, the direction that those beams are going, the number of scans that we're going to perform, and how those beams are put together through the focal law. But oftentimes through our codes, we don't get an idea on how to manipulate those essential variables. So the list that you're looking at right now, the part details, the probe and wedge that you're going to use, the focal laws that you build on the instrument, number of scans, the direction of scans, these end up being listed as an essential variable. But let's take a little bit of a deeper look at some of the codes that are out there that include phased array and require this information. So the first example that I have for you is probably an example of a code that's the furthest along when it comes to implementation of phased array, or at least a code that's done a lot of work with phased array. And that is ASME. And what you're looking at here is an excerpt from implementing phased array in accordance with Section 5, Article 4. A little difficult to read, but there's one particular paragraph that I just want to highlight here. And that is in the middle of this document, they require that a scan plan be built to implement an encoded phased array inspection. Great. We have a code that tells us we're required to do a scan plan. So what's involved in that process? Okay. And in that paragraph, and you may laugh at this, it says a scan plan shall be provided. And that is it. It tells us that we have to provide or show the search unit placement. We have to show where and how it's going to move. But the information that you are not given is the information that we originally came to look for. How many elements am I supposed to use out of the transducer? What beam angles are sufficient for a particular weld or joint design? Should I be using a linear scan or E-scan, or should I be using a sectorial scan? What about building the focal law and establishing a focal depth? This particular code tells us that we have to build a scan plan, but what it doesn't tell us is how to do it. In addition to ASME, we see very similar information in a couple of other examples. So I have two other examples that just for comparison purposes I put in here for you. So the next example would be AWS, which AWS is a little bit different because it requires some extra hoops that you have to jump through to implement it. And they require very similar information. So we have to establish a written procedure to use phased array. And again, very similar. They list out some essential variables for us here in the middle. And they list out how we scan it. Like if you look in the middle, thickness range, joint type, scan speed, what angles you use, so on and so forth. So they require that we document how we're doing the inspection, but they don't give us any guidelines on how to build the scan plan or how to properly evaluate or choose some of the variables that we talked about. The other example that I have is from API. Okay? And this particular excerpt comes from 1104. And again, it's very similar information. And this particular code section outlines how to perform phased array. And again, they require us to establish essential variables, but not how to put it together for the actual inspection. And they dictate that we determine the angles of inspection, how to approach it, how to choose the elements involved, but not a lot of guidance on actually how to put that together. So what do these three examples tell us about the scan plan? What it tells us is that we oftentimes have to come up with this information on our own. We either have to make sure we designate the personnel that has enough experience or knowledge to put the scan plan together, and that we find a good means to do so. So what I want to do, and what we've done for you, is we're going to go through and we're actually going to look at the steps that should be involved in putting together not just a good scan plan, but what we hope would be an efficient scan plan. And at the very least, point out some items involved that are important to pay attention to and what they will affect when it comes to your actual inspection. And what we want to start with is the equipment that's involved in implementing the scan plan. When you build a scan plan, you primarily have three different sections or three main variables involved. You have anything that will change with the part. So by the part, we mean the thickness of the part, the material type, the joint detail. Okay, so we have to include changes there. We have the selection of the probe and the wedge. So based on that part, the material, the joint design, we are then going to select the proper transducer and wedge. And probably the big one that we all think about, that we all look at immediately when we view a scan plan, is the actual focal loss selection. So trying to choose the beams that are appropriate, the appropriate scan type, sectorial or electronic scan, okay, and then perhaps looking a little bit deeper at the elements that we're using to do so. So our job is to try and take these three categories, if you will, and actually put them into a scan plan. Now there's a couple ways to do that, and as you see here, you can hand draw a scan plan, or you can use some sort of software program to develop the scan plan. The hand-drawn scan plans, very thorough way of building the scan plan. Thorough in that it involves the actual physical use of the equipment. So if you want to hand draw a scan plan like you see here on the right, okay, it requires you to take physical measurements of the part and translate that onto a to-scale drawing. So here on the right, you're looking at two different hand-drawn scan plans, one for a half-inch joint, one for a 1-inch joint. So it requires you to physically measure the part and translate that to a drawing. And it also includes physically using the actual inspection equipment. So you're looking at beam plots that were measured from an actual transducer. So the front of the wedge was plotted and the actual exit points were plotted. So you could guess that by looking at this that it's a little more time consuming. that because you're taking physical measurements, you're drawing it by hand, it is a little more involved there. But it also allows you to account for any errors that you have in that equipment. So if there is a physical difference between these exit points that you're marking, those might not be the same when you put those into a software program. So it takes a little bit more time. You are taking visual measurements by hand, so you do have a little bit of human error involved, but it's a little more accurate because it forces you to use the actual equipment that you'll use for the exam. Now on the flip side, you can also develop your scan plan through software. This would be through the couple examples I referenced at the beginning. NDT Setup Builder, Eclipse ES Beam Tool, okay? Much faster to use. It has all of the information for our equipment pre-programmed in to where all we have to do is draw the part or select the part from a pre-built database, and it works much faster. So for efficiency purposes, using a software program to develop your scan plan is a little bit easier. But what you lose is the differences in what the software has programmed in versus what you physically have in your equipment. If there are any differences between the equipment that you're using, such as dead elements in your transducer or irregular wedge wear, that won't show up in the software program. Oftentimes when phase array procedures are written and they cover scan planning, they'll require that any software scan plans developed be manually followed up, meaning you measure the exit points of the beams you're using and you make sure that those coincide with what the software gave you. So software, a little bit easier to use, but it doesn't account for the actual equipment. Now, in going about building the scan plan, so using the hand-drawn or using a software program, we have to start somewhere. Okay? Obviously, we are working to a specific part, so we should know the thickness of the part, we should know the material type, we should know the joint design. So where we have to start is the actual equipment. Okay? So we need to make sure that first and foremost, we're choosing the transducers that are proper for the material we're testing. So we need to consider differences in material type, such as maybe the difference between how our sound waves react to traveling through carbon steel versus traveling through some form of stainless. Okay? We need to consider the wedges that we're using. Okay? A big issue in phase array sometimes is the physical size of the equipment. Okay? Do you have the right access to get to the part? Is this large transducer here going to fit in a restricted area, or are you going to have enough surface to place that down? Those are some things that are fairly simple, but often get overlooked as part of the scan plan. And in addition to that equipment, you also want to make sure that your instrument is capable of handling any transducer or any wedge that you would like to use for the scan plan. So first, with the scan plan, we just want to make sure that we don't overlook the simple step of picking the right transducer and wedge for the material that we're about to test. Now, when we pick that equipment, specifically with the transducer, there's another significant step with the transducer that gets overlooked again, and that is how you are choosing or designating the elements inside of that transducer. So in this particular slide that you're looking at, every transducer is built a little bit differently in regards to how the elements are patterned inside of the transducer. Now this may not sound like too much of an issue, but depending on the spacing of the elements, how large the elements are, and how many of them you are using will affect the way the sound travels through the part. So we typically look at 4 factors involved in how the transducer is put together. As you can see on the left here, we look at the actual quantity of the elements. Are we going to use 10? Are we going to use 12? Are we going to use 16? That affects the outcome of putting the beams together. We look at the physical size of the element. Are we using a larger element, a smaller one? We look at how close together they are, the pitch value. Are those elements spread further apart, or are they closer together? And then lastly, we look at the elevation of each individual element. Are they wider or are they more narrow? When we put all 4 of these element or transducer characteristics together, we have different effects that come from what we call our VPA. So a key significant step in scan planning is determining the size of your aperture that you'd like to use, or taking the combination of those 4 transducer variables and putting them together. VPA stands for virtual probe aperture, which again is how many elements of the transducer you're using to establish your beams. And when we put all of that together, there are some key items that we look at to put that together. The first one that we look at is focusing. The size of your aperture will affect your ability to focus and how deep into a material you can perform that. In certain inspections, this would be important for, say, sizing. If sizing is of importance to you, say for sizing the height of an indication, you might want a transducer that has a larger pitch, meaning the elements are spaced further apart, and you would probably want to increase the quantity of the elements that you're using, such as the example on the left. Okay? The more elements you add and the larger they are, or the larger spacing there is, the more efficient the focusing becomes, and that might help you with height sizing. But as is with a lot of things that we talk about with UT beam characteristics, you often have a trade-off. And when it comes to scan planning and choosing the proper elements, another factor that we have to consider is our ability to steer the sound beams through different angles, and which is typically the goal of our phase array inspection, is to generate different angles to use to interrogate the part. And if you're looking at the elements inside of the transducer, if you need more steering capabilities to cover, say, a larger area or a bigger part, you would want a transducer that's capable of steering through a broader range. And in that case, you would want the exact opposite, meaning you would want a transducer with smaller elements and elements that are closer together, which is the exact opposite of what you would look for increased focusing capabilities. Again, these are some items that very often get overlooked during the scan planning process. Okay, very often we just pick a transducer that has an increased number of elements and matches the frequency that we want. Well, there's other things that we can adjust, that we can account for with the elements to give us better characteristics of our exam based on what we want to see. Okay? And these are a couple of items that you would want to factor in and keep track of. And lastly, with the equipment, you would also want to take into consideration what the surface or the shape of your part will do to your inspection. So in particular, also want to factor in if your part is curved or rounded. Say you're looking at a long seam on a vessel or a pipe. That requires placement of the transducer in the opposite direction, and like you see here. This boils down mainly to the size of the transducer and the wedge, where you would, in this case, maybe consider using a smaller piece of equipment to reduce the effect of the curvature. Whereas if you choose to use a larger transducer, you have to ensure that the contact is sufficient if you need to curve the wedge. And you also have to ensure that the focal laws are put together properly now that you are transmitting through a curved surface rather than a flat surface. So the point here is just make sure that you're not overlooking your surface condition of your part. Just making sure that you, again, select the proper equipment, not only for the beams, but also to make sure that those beams are transitioning into the part correctly. Okay? But once you have your equipment picked out and you've decided you're using such and such transducer, you've determined the proper wedge that you want to use, and you've isolated what elements and the size, spacing, and number that you'd like to use for the examination. Now what it boils down to is actually putting the beams together. So let's take a moment, look at what's a good process for doing that. What are some things that we consider when we would like to choose those angles? So when we look at this step in the process, we can look at this from two particular perspectives. One from kind of what I like to call a minimalistic approach, and one from what I like to call kind of an overhaul approach. From a technician standpoint, the scan plan just tells them what equipment to use and what beams to use. So whoever's building the scan plan has to follow some sort of criteria for picking the beams. And usually they fall into one of two categories. The first category ends up being what I like to call a minimalist approach, where you look at the code, and the code doesn't tell us much in terms of scan planning. All the code says is that we need full volumetric coverage plus the heat affected zone. So with this approach, that's all they did. They took the transducer, they set it back a certain distance from the weld, and they just set up beams to get full coverage. Very easy to do. Doesn't take much time to set up. You can collect the data real fast. But what was the purpose to doing this? The only purpose was just to satisfy the part in the code that says you have to have coverage. Why these particular beams and angles? Are those going to be of any benefit to you in finding a particular defect? Okay, the answer is I don't know, because all they did this for was for coverage. Now you could also take the opposite approach, which on the other end of the spectrum, you have this idea that we have no control over how the defect is oriented in the part. So if you take a three-dimensional look at a weld, the flaw is not always going to sit perpendicular to your sound beam. It may turn away from you. It may turn up and down. It may be transverse to you. If you take that approach of not knowing and not being able to rely on a particular orientation of a flaw, the only way to reliably detect it is to approach that indication from multiple positions. So this particular scan plan, that's what they've done. They've taken a very large transducer, placed it a set distance back from this weld, and instead of going just for coverage, they went for coverage from as many different positions as they could. So you're looking at 3 separate sectorial scans here. Okay? if you want to try to put some purpose to it, maybe they broke the weld up into 3 particular areas. Say the red one at the bottom third, the green one in the middle, the blue one's covering more of the top. But the point to this is to introduce as much sound into the part as possible from as many different positions as possible to improve your probability of detection. So this type of scan plan is going to give you excellent detection capabilities. It may give you a little bit of better resolution when it comes to sizing, but there's really no purpose to all of these beams here other than just to get as much sound into the part as possible. Keep in mind, however many beams, however many angles that you decide to create, the instrument has to account for all of those beams. So all of these angles, all of these beams in this part have to be calibrated. They all have to be analyzed when they take the data, and that eats up time. It's not as efficient. And we could improve upon this. We could put better purpose to this. So that's what we try to do. We want to put more purpose to the beams that we choose for the scan plan. We have a particular process that we use, that we teach for developing a scan plan that essentially asks 2 different questions about what you're inspecting. So we need sort of a plan of attack, sort of a different means of inspecting the part, other than just looking at pure coverage. So we want to look at the important areas of our part, or what are the critical zones or areas of that part. And we want to look at them individually and ask, are there any flaws that are specific to this area? And are there any beams or angles that will best reveal that indication? So we've taken this and we've implemented it for a generic weld inspection. So we realize that there are going to be specific types of defects that are more prevalent to different areas of the part, and we realize that there are better angles than others for detecting those defects. So we've taken our weld and we've broken it down into 4 critical areas. We've broken the weld into the root. We've broken the weld into the fusion zone or the bevel. We've broken it into the heat affected zone coverage. And then last but not least, we identify the overall volume of the part. So we'll run through these 4 areas and kind of highlight why we look at them separately and what we want to look for in each one. What this means is we basically treat our scan plan like a checklist. So we set up our beams to look at all 4 of these areas individually. If you can cover these 4 areas from one position with one set of beams, then one scan is all you need. So as you see at the bottom here, we have 4 areas of coverage, but that doesn't necessarily mean you're going to have 4 separate scans of the part. All this means is we just have 4 specific areas that we want to look at. So let's kind of just take these 4 areas and look at them in particular. The first is the weld root. So again, we take these 4 areas and we ask primarily, what are we looking for in that area? And are there any angles in particular that are better for finding those types of defects? So with our weld root, we have a lot of variability in flaw type there. So if we look at our list here in the middle, we've got lack of penetration that we can find. If we're looking adjacent to the root, we can have cracking next to there. In our example of the double V weld, centerline cracking can be a problem. So we have some variability in not just flaw type, but flaw shape. Now we consider this a important area of the joint because this is where the joint originates. This is where the welding process begins. So we designate this as a critical area, but because we have so much variability on the flaw type, the one thing that we want to make sure we do is that we interrogate this area first. And we try to get to this area first leg if we can. Moving on, we branch that to the fusion zone. Now in the fusion zone, we aren't looking at the volume of the weld. We aren't looking at the base material, so we're focusing specifically on the side or the bevel of the plate material. Essentially, what we're looking for is sidewall lack of fusion. Okay? Or, obviously, we can get very specific with different defect types. Okay? So you could include sidewall cracking. Obviously, we know you could get slag that ends up being very tight to the bevel. So obviously, we do have some different things. But the point with this area is that it needs to be covered with very specific angles. If we don't choose the right angle to cross the bevel or the fusion zone, then we aren't perpendicular and we don't get as much sound return. So based on a key study that was done in industry, what we found out is that with phased array, we can vary the angle quite a bit with sectorial scans. As you see down here at the bottom, we can vary the angle plus or minus 10 degrees. And we can vary the angle with our electronic scans or E-scans about plus or minus 5 degrees. So how does that work? How do you implement that? In this example, we're looking at a single V weld that has a 30-degree bevel prep. And if you take a 60-degree beam, that will hit a 30-degree bevel prep perpendicular. So in this example, what they've done is they've set up the transducer to take that 60-degree angle and hit it perfectly in the middle. Our criteria said that we want to try to stick to plus and minus 10 degrees. So the 50-degree beam that they generate from this sectorial hits the fusion zone at the top side. So there's our minus 10. We then add plus 10, and now our 70-degree beam intersects the fusion zone at the bottom. That way, no matter where we're looking on this fusion zone, we have an optimal angle to interact that bevel. And hopefully, get a reflection back and see an optimal signal. Continuing on, we have the heat affected zone coverage. So the heat affected zone looks at specifically the base material adjacent to the weld. Again, what type of flaws are we looking for in that area? Those flaws are going to be essentially cracking. With this area, we've decided that it would be best to choose specific angles for that area. So in the middle, what we've designated is that you attempt to use somewhere between 35 and 58 degrees. We choose those particular angles because of their ability to properly place a corner trap type signal in the proper location. Meaning if a crack ends up being connected to either the ID or the OD surface, those particular angles are better for determining that it is surface connected. To highlight that a little bit better, this doesn't mean that you can't use anything above 58 degrees. We're not trying to eliminate the higher angles from interrogating or evaluating cracking. We use these particular angles because they best reveal a surface connected defect, which if we're trying to look for or determine surface breaking cracks, we would want to make sure that we do position those correctly. Last but not least, we have our final criteria that we look at, which is our volumetric coverage. Now, I usually laugh a little bit about this particular area because we kind of get a little lazy with it. In the volume of the material, discounting the bevel or the fusion zone, discounting any defects that you would have included in the base material or the heat affected zone, if we look at the full body of the weld, we're typically looking for more volumetric type indications or more rounded indications. Normally, or in most cases, those end up being what we like to call omnidirectional reflectors, which in a nutshell means that no matter what angle you use to approach these reflectors, they tend to give you a similar response. So if I choose 70 or 60 or 50 or 40 degrees and I look at a rounded type of indication, the amplitude is going to be fairly consistent. Now obviously that'll change inside of a part. We know that flaws move a little bit, but in most cases that's what we find with volumetric type indications, which is what we're looking for in the body of the weld. So here, what we look for is just to ensure that the full body is sufficiently covered. And that is the 4 pieces of criteria that we try to use to develop the scan plan. So what I would like to do is just kind of show you how this is put together, how you actually take this and build the scan plan, and give you a bit of an example. So bear with me just one second. And I am going to pull up my program, and we'll start with NDT Setup Builder. So here we have a 3/4 inch single V weld. So a pretty basic, pretty simple example to utilize. And we've got 2 transducers here. So I'll try to show you 2 different examples of how to build the scan plan. So we'll start with how you would use or build, say, a sectorial scan. So what I'm going to do is I'm going to add a beam set to this part. Now we have 4 areas that we have to cover and 4 areas that we have to cover properly. I want to make sure that I'm putting purpose to these beams and that they're actually being used for something in specific rather than just making sure that there's coverage. Normally the way I start this process is I start with the bevel because that's the area that's more tied to those particular angles. So what I'll do is this is a 30-degree bevel, so I know that I need angles from 50 to 70 degrees. So I'm using a sectorial scan. Here's the 50, here's 70. So what I can start with is just ensuring that I've got these beams properly placed. That would be okay. The bevel looks like it's covered quite well. And I did that by changing which element I'm starting with. Now, from there, I would have to look at the rest of my criteria. So I have the root to consider. I have the heat affected zone to consider. One thing that I can do is I can add or remove angles from the beam set to interrogate the rest of the area. Now, I want, as best as I can, to cover the heat affected zone at the OD and the ID with those specific angles. Those specific angles being somewhere between 35 and 58. So with this position, I would be covered quite well at the top, but maybe not covered quite so well at the bottom with the angles that I want. Now, there's nothing in our code book that is going to require me to do what I'm about to do, but I'm going to do it just to get a better look at the part. And what that is I'm going to move this beam set forward and try to get more of the ideal angles that I want at the bottom. And what I can do in a simple phased array examination is I can always add a secondary beam set for the rest of the heat affected zone coverage that I want up here. So to review and go back through my list, I needed the root covered first leg, which I have here with approximately, oops, wrong one, sorry. So I'm intersecting the root right now with a 65-degree angle. I needed the bevel face covered with angles from 50 to 70. So if I adjust my angles, with this blue one by itself, I'm short, but I will add to that a secondary scan at the back to make sure that's overlapped with the right angles. I needed my heat affected zone covered with particular angles, so I have that at the bottom and at the top by combining both sets. And normally by making sure that those three areas are covered, the root, the bevel, and the heat affected zone, my volumetric coverage falls into play as well. This is a little bit more difficult to do with linear scans because they don't offer as much coverage. So if I wanted to try and carry this out with linear scans, I really have to pay attention to where these beams go and make sure that I'm actually getting the right amount of coverage. So again, if I start with the bevel, I have to be careful with how close I put the transducer. I have to make sure that the right angles are hitting the bevel face, plus the root, plus the heat affected zone. So what you end up having to do with linear scans is you have to end up adding more and more and more to get the specific areas that you need covered. So what I'm doing is I'm adding a secondary linear scan to try and get the coverage of the root, making sure that the bottom part of the bevel that I was covering was correct, but now I end up being short with my heat affected zone at the top. So if I wanted to cover this simple single V joint with linear scans, I end up actually adding 3 separate linear scans, each one at different angles, to get that coverage. So now I have the top, the bottom, the bevel, and the root covered again. A little more complicated, a little bit harder to do with linear scans. And in addition to that, we often don't get very simple drawings and parts to do scan planning for. So I've transitioned to the beam tool program just to give you a different perspective of what programs are used for to do this. And what you're looking at is you're looking at a transition joint. So you have a 1/2 inch part welded to a 1.5 inch part with a very, very vertical bevel on the weld, plus you have a backing bar. So this is every UT data analyst nightmare. You have different material thicknesses, you have a vertical joint prep, and you have a backing bar that you have to deal with. So you end up having to do very similar things in changing how you intersect that area with either different sectorial scans, making sure that you really change up the angles that are interrogating those areas. And on this side, from the transition side, you really have to pay attention to what you're using for the elements and how many beams you're dealing with here. Not just the angle, but again, how you get those angles. But once you have these scan plans in place, oftentimes you have to transition that to somebody that has to review it, look at it, analyze that. So it's very nice with these software programs that have built-in reporting tools. So these programs allow you to take these scan plans and transition them into a report format that you can then show either the client, the inspector, and give them the step-by-step instructions on what you were testing, what you were using to test, and how you actually put together the beams, the elements, the position of the transducer in order to do the inspection. So this gives you a good layout for how that scan plan was implemented. And that's always an interesting step in the process. So if you will give me just 1 minute, what we're going to do at this point is look at some of the questions that you've submitted. And what we'll do is we'll take some time just to answer some of the questions that you've posted. So give me 1 minute, we'll review the questions, and we'll start a little Q&A session. All right, thanks for waiting. We do have a few questions that we'll address. We had quite a few submitted, so we'll answer what we can get to. We are running a little short on time, so if we don't get a chance to answer your question, we will do so through email, and we'll contact later if your particular question didn't end up getting answered. So a couple of questions that I got through. One was, is scan planning required for other materials or other applications? Scan planning, you end up performing really regardless of the type of material or the type of application. So it's always important in a phased array inspection that you do address some form of a scan plan. So do you have a different type of material or it's not a weld? Yes, scan planning is important. One big question, I get this one quite a bit actually. Question was, who is considered qualified to build scan plans, or are there any scan plan certifications? Normally where you would get this information, so do you have to be qualified to build a scan plan, would be to reference your code for that. Most of the codes designated that you have to have a scan plan, but they don't put any additional qualifications to personnel that build it. Other than that the scan plan is part of your procedure. The procedures are typically developed by level 3 personnel. So typically that responsibility ends up falling to whoever is building the procedure would also build the scan plan. But at the very least, you would want to make sure that whoever is evaluating or building scan plans obviously has the necessary knowledge. One question I got, is scan planning required for manual inspections, or is it just required for encoded inspections? The difference between using phased array for manual, using phased array for encoded, that often also boils down to what your code designates. For example, ASME inspections separate manual from encoded inspections. Per code, they require scan planning for encoded, but they do not require it for manual inspections. Now, does that mean you don't need to do a scan plan? Well, not in the documented sense, but in the performance sense, yes. You would want to perform a scan plan at least to determine some of the things that we talked about, equipment placement, how you pick the elements, so on and so forth. So Do you need to do a scan plan for manual inspections? Not technically documented through code, but is it a good idea? Yes. And then one last question. I got one that says, are any of the codes planning on expanding their scan planning requirements? So this is a big kind of hot button topic on scan planning. I have talked to a few key individuals. ASME in particular is planning on expanding how they define scan plans and setting some base requirements for how you build them, how you document them, and what information has to be included. So yes, as we all know, our codes are ever evolving, ever changing, and scan planning is definitely included in some of that expansion. So are we going to see some changes to scan planning from a code perspective? Definitely. Well, I think that is all the time that we're going to have for you guys this afternoon. Again, thank you to everyone for taking the time out of your day to check out what we have and the information that we provided. Again, I appreciate it very greatly. So at this time, I'll turn it back over to Greg.
Thank you, Curtis. Nice job. On behalf of Olympus, I'd like to thank all the attendees for joining us today, and Curtis for his expertise and participation in today's event. We hope this material presented was informative and useful. This webinar, along with the Q&A session, will be archived on the Olympus website at www.olympus-ims.com by the end of the week. Everyone who registered for this event will receive a follow-up email with links to the archived presentation. That's going to do it for today. Thanks again for attending, and we'll see you again next time.